Part 3 of the additional aspects of equilibria. This is solubility equilibria that we're going to talk about. So, I know I told you in the beginning that ionic compounds, there's certain ionic compounds that are insoluble, right? Well, in truth, all ionic compounds are slightly soluble. They're always slightly soluble in water. Some of them dissolves, right? Just because of the likelihood of that happening when you have such a large number of particles. Because remember, atoms and molecules are really, really tiny. So calcium fluoride is pretty insoluble, right? But when you have calcium fluoride solid, some of it will dissolve, right? And you get calcium ions and you get fluoride ions, right? So the equilibrium expression would be calcium ions, because they're on the product side, times the concentration of fluoride ions squared, because the coefficient is 2, right, divided by the concentration of the reactants, which is calcium fluoride. But solids are not included in equilibrium expressions, so the K of this kind of thing, of calcium fluoride dissolving in water, would be equal to the concentration of the calcium ions times the concentration of fluoride ions squared. So this is called a KSP. SP stands for solubility product. The reason why it's called a solubility product is because it generally doesn't have any reactants in it, so it's just the product of the two products of the reaction. So there's a couple of terms here that I want to go over. There's KSP, or solubility product. That is the equilibrium related to solubility. Solubility itself, when it's just deemed solubility, is typically in units of grams per liter. So if you're looking up the solubility of a substance, it'll often list it in grams per liter. However, we're going to find molar solubility to be the most useful, because molar solubility is in moles of solute per liter of solution. So here's an example. So how would you calculate the solubility product from the solubility? So if you're given a situation where you have silver chromate added to pure water, so the silver chromate is added to pure water, and then you find that the concentration of silver ion in the solution is 1.3 times 10 to the minus fourth molarity. I love how in this example they say the mixture is stirred for several days. Like, that's actually going to be a thing, but whatever, that's fine. So assuming that your silver chromate dissociates completely in water and that there are no other important equilibria involved, meaning that this is the only thing that we got to worry about, is this silver chromate dissolving, right? The splitting apart into its silver ions and chromate ions. Okay, that is what we're talking about. And then they find out that the concentration of silver is 1.3 times 10 to the minus fourth. So when you write out the solubility expression, you have silver chromate solid dissolves into 2 silver ions and then a chromate ion, right? The KSP is going to be this concentration of silver squared, because 2, right, goes up here, and then times the concentration of the chromate. So to calculate KSP, you're going to need the equilibrium concentrations. So you set up the equation because it tells you that the equilibrium concentration of silver is 1.3 times 10 to the minus fourth molar, right? So to figure out the concentration of chromate, you use the stoichiometry from your equation, and you know that there's 1 mole of chromates for every 2 moles of silver, so 6.5 times 10 to the minus fifth molarity is going to be the concentration of the chromate. Plug that back into your equation. 1.3 times 10 to the minus fourth squared times 6.5 times 10 to the minus 10th is going to be your solubility product, your KSP, which is 1.1 times 10 to the minus 12th. Okay, so that's your example. Here's another example. How would you calculate solubility from KSP? So if you get the KSP, which you can look up in the back of any textbook, is for calcium fluoride is 3.9 times 10 to the minus 11th. So that means for every, quadrillion, million, trillion. So it happens once every trillion molecules or so, right? Assuming that the calcium fluoride dissociates completely in dissolving, right? You got no other equilibria involved. So here's your rice box, right? The reaction has the calcium fluoride goes to calcium ions and 2 fluoride ions, right? That's your reaction, if you will. The initial concentration is, of course, 0 because nothing's dissolved. And then there's a change, right? So the calcium ions are going to change by some X value, right? Fluoride ions are going to change by some 2X value because there's a coefficient of 2 in front, right? So at equilibrium, the concentration of calcium ions is going to be X. Concentration of fluoride ions is going to be twice that, right? So then you set up your KSP, and so that's X, the calcium ion concentration, times 2X, the fluoride ion concentration squared, right? So you do that. If you do that and you square 2x, you get 4x squared times x gives you 4x cubed. Then you take your number here, divide it by 4, take the cube root of that, you get 2.1 times 10 to the minus 4th molar. So that is your molar solubility for calcium fluoride. And if you wanted to convert that into gram solubility, you would have 1.6 times 10 to the minus 2 grams of calcium fluoride per liter of solution. So that's the important part, right? Now there's some factors, of course, affecting solubility that's important, right? Most of them are viewed as Le Chatelier's principle effects or kinetic molecular theory effects, like particles in motion, and that kind of thing. So you guys understand, hopefully, Le Chatelier's principle so that you can understand how this works. This is another illustration of amphoterism. We talked about that before, how you have metal oxides and metal hydroxides that their solubility changes depending upon the pH, and that's a Le Chatelier's principle. But it also involves metal complex ions, and we're not going to talk about metal complex ions till later on after the test, if you want to. And that's what this slide is all talking about, complex ion formation. So I'm going to pause here. I'm going to say, okay, it's really important that you are able to do problems number 47, 49, and 53 on the homework, right? The last problem in the homework is just kind of silly. I don't know why I put it there or why I kept it there. It doesn't make any sense. But so if you want to do that before I show you the answer key, pause now, and then you can start it up later. So here's your answer key for the homework problems. Question number 47 asks, why is the concentration of undissolved solid not explicitly included in the expression for the solubility product? Well, that's of course because the concentration of a solid doesn't change, right? Solid's either there or it's not there. And then the expressions for each of these reactions is right here, right? So silver iodide, you would break apart into silver ions and iodide ions. Vitally important that you remember from Chem 1 that polyatomic ions generally stay as polyatomic ions when they're dissolving in water, right? So strontium sulfate would break apart into strontium and sulfate. If you're having a tough time remembering which ones break or how it's going to break down, just name the compound. And once you name the compound, you have cation, anion, and then you know how it's going to break down. Okay, iron hydroxide, so you have iron and then hydroxide ions. This one's funky, the mercury 2 bromide. Mercury 1 bromide, I'm sorry. Mercury 1 bromide is funky because it's a diatomic ion. Don't worry about it. You're not going to come across it in real life. If you do, it's a really bad situation and you're specifically a mercury chemist. So don't worry about that too much. 49. So 49 is a good one because it gives you solubilities and then you have to calculate KSP. So that's what I'm doing here. Just plugging in numbers, right? And then it's important to know, stoichiometry. And so when you have 2 moles of fluoride ions here, then you're going to have to double the concentration of calcium ions because it's going to be 1 calcium ion for every 2 fluoride ions. And then you also make sure you square that because there's a 2 in front in the balanced equation for the reaction. I didn't write the reactions here, but you hopefully you figured that out by now, right? We wrote the reactions up here, so I didn't write the reactions down here. And then we have molar solubility of silver bromide in different situations. So I just did the pure water is just the same as what you did before. But here we have in silver nitrate solution. So if it's in silver nitrate solution, the silver ions, that's going to be a common ion effect, right? So the concentration of silver that dissolves is going to be equal to the concentration of silver from silver nitrate plus however much silver bromide dissolves. And so that's going to give you the 3.0 times 10 to the minus 2 plus x over here. I didn't do a rice box for this. specifically on this paper, just because rice boxes take me a long time to write on the computer. If you need, a rice box, we can go over that in the conference. Okay, and then the same thing with sodium bromide. Notice that here you have bromide, which is the common ion to silver bromide, right? And so you're going to do the same thing down here. Notice that the concentration or the solubility of it dramatically decreases, right? So you have pure water at 7.07 times 10 to the minus 7th. That's not really terribly soluble, but then when you go down to silver nitrate solution, it becomes much less soluble, and then in the sodium bromide solution, much, much less soluble, right? So that's the idea there. So I'm going to stop here, and you are completely done with the chapter 17 stuff that you absolutely need to know, right? And even some of this was bonus knowledge. But from here on out, I want to talk about bonus knowledge. So if those of you who want bonus knowledge and application of these ideas, please continue to listen. If you don't, then you're good and you can stop here and you should have everything that you need. Okay, so I'm going to go back to the PowerPoint, and then precipitation and separation of ions. So this is selective precipitation of ions. You can do this based upon the different solubilities of the ions. This is a pretty advanced chemistry topic. Just know that the ion, if you have two ions that are in solution, and you're trying to precipitate one of them, for example, if you had silver and copper, right? Silver is much, much less soluble than copper is, right? So if you added sodium chloride or hydrochloric acid to a solution that was made up of silver ions and copper ions, you would precipitate the silver, and then you would be left with copper in solution. And then you could do that precipitation later. So it's a really cool practical application. So let's say you had a mixture of lead and silver, right? What would you do? Which one would precipitate first? You have the solubility of silver chloride is 1.8 times 10 to the minus 10th, and the solubility of lead chloride is 1.7 times 10 to the minus 5th. Notice those are not really big KSP values, right? But one of them is much lower than the other one. So which would precipitate first, silver or lead? I'll give you a second. That's right, the answer is silver, because it is a lower KSP and it would be less soluble, okay? And then finally, one last piece of bonus knowledge, there's quantitative analysis for metallic elements. This used to be a mandated lab in AP chemistry. We used to have to do this lab, but we don't anymore. It's pretty hard to get like a really good right answer. But if you are going into environmental chemistry, or if you're doing analytical chemistry in the future, this is something that you are going to do in life, right? So because it's something you're going to do in life, you're probably going to do it in college too. So I don't want to bore you with it, but if we were face to face, this would be a fun lab to do, where I give you a mixture of a bunch of things and say separate it into all the different metals that you can, and tell me what's in it. And you can follow like a flow chart similar to this, right? Where you add hydrochloric acid, then you add hydrogen sulfide and hydrochloric acid, and then you add ammonium sulfide and change the pH, and then you add ammonium hydrogen phosphate. Oh, so great, so great. And then you precipitate a bunch of stuff, and then somewhere along the way you would dissolve the things that you got, and then you would do flame tests, and super cool. And if you think it's super cool, then chemistry is the right place for you to be studying. If you don't think it's super cool, then you're just normal. Yeah. So I hope you enjoyed this. Remember, this last part, the last section of this, section 6 and section 7, were applications and bonus knowledge. I'm not going to ask you specific questions on these on the tests, but I thought it was fun. So let me know if you have any questions, and good luck.